The Oxford calculators were a group of 14th-century thinkers, almost all associated with Merton College, Oxford. For this reason they were dubbed the Merton School. These men took a strikingly logico-mathematical approach to philosophical problems. The key calculators, writing in the second quarter of the 14th century, were Thomas Bradwardine, William Heytesbury, Richard Swineshead and John Dumbleton. These men built on the slightly earlier work of Walter Burley and Gerard of Brussels. Science. The advances these men made were initially purely mathematical but later became relevant to mechanics. They used Aristotelian logic and physics. They also studied and attempted to quantify every physical and observable characteristic, like heat, force, color, density, and light. Aristotle believed that only length and motion were able to be quantified, but they used his philosophy and proved it untrue by being able to calculate things such as temperature and power. They developed Albert in his work on trigonometry, and the most famous work was the development of the mean speed theorem, which is known as the law of falling bodies. Although they attempted to quantify these observable characteristics, their interest lay more in the philosophical and logical aspects than in natural world. They used numbers to philosophically disagree and prove the reasoning of why something worked the way it did, and not only how something functioned the way that it did. The Oxford calculators distinguished kinematics from dynamics, emphasizing kinematics and investigating instantaneous velocity. They first formulated the mean speed theorem. A body moving with constant velocity travels the same distance as an accelerated body in the same time if its velocity is half the final speed of the accelerated body. The mathematical physicist and historian of science Clifford Truesdell wrote, "The now published sources prove to us, beyond contention, that the main kinematical properties of uniformly accelerated motions, still attributed to Galileo by the physics texts, were discovered and proved by scholars of Merton College. In principle, the qualities of Greek physics were replaced, at least for motions, by the numerical quantities that have ruled Western science ever since." The work was quickly diffused into France, Italy, and other parts of Europe. Almost immediately, Giovanni di Casale and Niccolò Osma found how to represent the results by geometrical graphs, introducing the connection between geometry and the physical world that became a second characteristic habit of Western thought. In Tractatus de Proportionibus, Bradwardine extended the theory of proportions of Eudoxus to anticipate the concept of exponential growth, later developed by the Bernoulli and Euler, with compound interest as a special case. Arguments for the mean speed theorem require the modern concept of limit, so Bradwardine had to use arguments of his day. Mathematician and mathematical historian Carl Benjamin Boyer writes, Bradwardine developed the Boethian theory of double or triple, or, more generally, what we would call n-tuple proportion. Boyer also writes that the works of Bradwardine had contained some fundamentals of trigonometry, yet Bradwardine and his Oxford colleagues did not quite make the breakthrough to modern science. The most essential missing tool was algebra. Thomas Bradwardine was born in 1290 in Sussex, England, an attending student educated at Balliol College, Oxford. He earned various degrees and was an English cleric, a scholar, a mathematician, and a physicist. During his time at Oxford, all of his works on logic, mathematics, and philosophy were written. He authored many books, including De Geometria Speculativa, De Arithmetica Practica, and De Proportionibus Velocitatem in Motibus. Aristotle suggested that velocity was proportional to force and inversely proportional to resistance. Doubling the force would double the velocity, but doubling the resistance would halve the velocity. Bradwardine objected, saying that this is not observed because the velocity does not equal zero when the resistance exceeds the force. Instead, he proposed a new theory that, in modern terms, would be written as, which was widely accepted until the late 16th century. William Heytesbury was a bursar at Merton until the late 1330s, and he administered the college properties in Northumberland. Later in his life he was a Chancellor of Oxford. He was the first to discover the mean speed theorem, later, the law of falling bodies. Unlike Bradwardine's theory, the theorem, also known as the Merton rule, is a probable truth. His most noted work was Regularly Solvendi Sophismata. Sophisma is a statement which one can argue to be both true and false. The resolution of these arguments and determination of the real state of affairs forces one to deal with logical matters such as the analysis of the meaning of the statement in question, and the application of logical rules to specific cases. An example would be the statement, the compound H2O is both a solid and a liquid. When the temperature is low enough, this statement is true, but it may be argued and proven false at a higher temperature. In his time, this work was logically advanced. He was a second-generation calculator. He built on Richard Clivingston's Sophistomata and Bradwardine's Insolubilia. Later, his work went on to influence Peter of Mantua and Paul of Venice. Richard Swineshead was also an English mathematician, logician, and natural philosopher. The 16th-century polymath Girolamo Cardano placed him in the top 10 intellects of all time, alongside Archimedes, Aristotle, and Euclid. He became a member of the Oxford Calculators in 1344. His main work was a series of treatises written in 1350. This work earned him the title of the Calculator. His treatises were named Liber Calculationum, which means Book of Calculations. His book dealt in exhaustive detail with quantitative physics, and he had over 50 variations of Bradwardine's law. John Dumbleton became a member of the Calculators in 1338–39. After becoming a member, he left the Calculators for a brief period of time to study theology in Paris in 1345–47. After his study there, he returned to his work with the Calculators in 1347–48.